So I think it's been a great conference, and I want to congratulate Tyler and Susan and everybody in the Singularity Institute for pulling this together. I'm quite proud of it, having founded the Singularity Summit with Tyler 2 years ago. And it's been a very content-rich conference, so I've taken a lot of notes, and I had thought I would spend a few minutes responding to some of the things that were said and discussed, but I wrote so many notes that I may not have time for many of my slides, but that's okay, you've seen them before. So I'm actually, when I get to my slides, I'm only going to show you some new slides we put together for the summit. My book came out in 2005, and it had these exponential graphs through 2002, so we thought for the Singularity Summit we ought to update them to 2007. And I actually did not have much anxiety as to whether or not these exponentials were holding up, and they have, and it's actually pretty amazing to me. And I have some theories that, we use the latest tools to create the next, and that's why there's exponential growth, but it really is pretty remarkable to me how inexorable this progressions turn out to be. And I've been tracking this for 30 years, and every time I update it, despite the fact that these curves are not some tabletop experiment of physics or a government-mandated program, this is just what happened from the, you would think, unpredictable competition of millions of people and IPOs and bankruptcies, recessions, the Great Depression, etc. And this exponential progression of information technologies in many different areas continues to march along. But anyway, let me start by going through the presentations and just making some comments on some of the things that were said and discussed. So Werner said, if you're writing the curve, the singularity will seem banal. And I agree with the basic thought there, that if you're writing the curve and therefore enhancing yourself and plugging yourself into the advancing technology, it will seem like reality, just as we kind of take for granted things today. We don't get from here to the future in one big leap. And then people question, well, do I really want to go there, when they hear about what the world may be like 30 years from now. We get there many steps at a time, and it's pretty remarkable actually how quickly people accept a new treatment for disease or a new communication paradigm, and it will seem like ordinary reality if you're riding the curve. But the point that I would make is that we're all going to ride the curve. I just got back from China. Half of the farmers in China have cell phones, and they're not just cell phones, they are web-enabled devices that allow the farmers in China to access all of human knowledge, and they're doing that, and they're creating new knowledge. Cell phones, web-enabled, are ubiquitous in Africa, and I'll talk a little bit more about this when I show you my slides, but ultimately these technologies become ubiquitous when they work. If you remember 15 years ago when someone took out a cell phone, or a mobile phone, satellite phone as they were called, there was a signal from the director, this person's a member of the power elite, because only a very wealthy person could afford a mobile phone, and they were the size of a brick and didn't work very well. And today that they actually work well and do a lot of things like access all of human knowledge, they are ubiquitous. It took us 10 years to put out the first billion cell phones, 3 years to put out the second billion. We put out the third billion in the last 12 months. We'll put out another 3 billion in the next 2 years. These technologies ultimately become ubiquitous. And it does address poverty. The World Bank reported that the poverty rate in Asia has been cut in half over the last 10 years because of information technology. Will be cut by 90% over the next 10 years at current rates. Other areas of the third world, like Africa, are actually only slightly behind. Their growth rate is greater than the developed world. These technologies ultimately become ubiquitous, and the economic statistics don't fully factor them in, because they talk about $1 of products, but $1 of computation today is a billion times more powerful than it used to be. In fact, when I was a student at MIT, well, I went to MIT in 1965 because MIT was so advanced at that time that it actually had a computer, and all of us were able to share it, and it took up a building. Well, the computer in your cell phone today is 1,000,000 times smaller, 1,000,000 times cheaper, and 1,000 times more powerful, and we all have them, or at least half the world literally has them. That's a billion-fold increase in price performance that we've seen. But it comes, one little step at a time, and so it kind of sneaks up on us. There was a question to Werner about climate change, and I will show you some brand new slides that just came from a National Academy of Engineering study that I did with Larry Page. We were part of a panel and asked to address the climate change and environment problem and energy. And we came up with a plan, which the National Academy of Engineering has published, to move to solar energy. And there's an exponential underway there. Now that we're applying nanotechnology, which is a form of information technology, to new materials and devices, and solar panels are coming down, and I'll show you that. And fossil fuels are going up, despite the recent bubble in fossil fuels. And the crossover, conservatively, is within 5 years. And the amount of solar energy we're producing has been doubling, not every year, but every 2 years, for the last 20 years. And it's easy to dismiss these things, just as the internet was dismissed, or the Genome Project was dismissed, when it's only 1% or a fraction of a percent. But it is now close to 1%. It's about 8 doublings away from being 100% of our energy needs. And there's 10 to the 17th watts that hits the Earth every moment. And we only need 10 to the 13th to meet 100% of our energy needs. And there are nanotechnology advances in both the storage devices needed to deal with the intermittency of solar energy and the solar panels themselves. They ultimately will be dramatically less expensive than fossil fuels. And within 20 years, at 8 doublings, 2 years, we will be really meeting all of our energy needs from solar energy. Well, there's actually similar scenarios for other renewable forms of energy. And so I'm actually very confident that we will address that resource need. And there's similar stories on other resource needs, which other aspects of this National Academy of Engineering study addressed, like water and food and so on. Nova Spivak talked about, well, if Moore's law holds up, and then had a discussion about that. And I do want to make the point, the basic point, that the law of accelerating returns, which I've talked about, is broader than Moore's law. Moore's law is really just one example of many within computation. And Justin, in fact, talked about how we go from one paradigm to another. The exponential growth of computation started with the 1890 census, the first American census to be automated. And we went through 5 different paradigms. Moore's law was not the first, but the 5th paradigm to bring exponential growth to computing. And this exponential growth, which again is amazingly smooth, through the entire 20th century, despite all the history, 2 great wars, the Cold War, the Great Depression, a lot of other things happened. And that exponential growth started decades before Gordon Moore was even born. And it's not just Moore's law, which is the shrinking of component sizes on an integrated circuit. Lots of other technologies that aren't even based on Moore's law, like magnetic data storage, genetic sequencing, where that was helped in the later stages by more powerful computers, but the basic technologies of scanning DNA have all improved. It's a basic phenomena when it has to do with information technology. He asked whether quantum computing is required, and Neil Gershenfeld commented on that it appears everything that goes on in the brain is either classical or at least can be created by classical means. If there's quantum computing going on in the brain, and there's actually no evidence for that, and the more we do brain simulations, it does not appear that quantum computing is required. But if it is, that would just demonstrate that quantum computing at a meaningful stage is feasible. And And then Nova talked about getting to human-level AI and then moving beyond it. And I would point out that once we actually can achieve all the capabilities where humans now exceed machines in a machine, that will necessarily be superhuman already, because if you think about all the things that computers can do that exceed human intelligence today, it's quite formidable. I mean, a mathematician can't hold up to Mathematica in terms of solving theorems and doing other types of transformations. We routinely access all of human knowledge with search engines, and your $500 computer can remember billions of things accurately, share knowledge at electronic speeds. You combine those advantages with our basic advantage, which is in pattern recognition, and that's actually my field of interest. That's a very powerful combination. And we are making steady progress in that. Actually, as I mentioned that, I'll just mention one example. Chess is often thought about as just an example of the combinatorial brute force advantage of computers, so they can think through all the move, counter move situations, and that's basically how Deep Blue worked. And I actually proposed to that team that why don't you use more pattern recognition to do the terminal leaf decision, because it's not just a brute force. You can't actually expand the entire game. You've got at some point abandon one of each of these trees and each of these branches in the expanding tree of move, counter move situations. And they did that in a fairly simple way in Deep Blue. And humans, Kasparov was asked, how many moves do you think about per second? Because Deep Blue did 300 million a second, and he said about one. So, how is it that he could hold a candle, come close to defeating Deep Blue, even though he was defeated by it? It's because of his deep powers of pattern recognition. He can evaluate that terminal leaf situation with a lot of pattern recognition capability. Well, that's exactly what the chess field has done. And today, computers running on a couple of personal computers can defeat the World Chess Championships with about 1% of the computation that Deep Blue had. And it's because of advantages in pattern recognition. Esther Dyson talked about genetic therapy. As I mentioned in the dialogue we had earlier, that is in fact coming along. Now that we have new tools, and now that biology has become an information technology in the early stages, and as I mentioned briefly, I'm involved with an exciting project where we take cells out of the body, and these are lung cells, so we scrape them out of the throat, and then in vitro add a new gene using some new techniques and some new microscopy methods, inspect that it got done correctly, inspect that there are no other genetic errors. That's been a problem with gene therapy. By sending in viruses with new genes, which was the old technique, that had a lot of problems. It would trigger the immune system, the gene would end up in the wrong place, and it would be deposited on a cell that had other genetic errors that you didn't really want to encourage. So we can actually inspect it in vitro, but making one cell with a new gene isn't very useful. So another brand new technology is to replicate that cell a millionfold, and then inject it in the body and goes through the bloodstream. And then, since these are lung cells, they end up back in the lungs, and this is cured a fatal disease, and it's undergoing the approval process. And it's actually one of several hundred developments like that. There's also about 1,000 drugs in the development pipeline using RNA interference, another brand new technology that allows us to turn genes off. James Miller talked about don't miss out on utopia. Well, my own feeling is I don't want to miss out on the singularity, but I wouldn't describe it as utopia. It might sound like that because we will have the tools to overcome the problems that we struggle with now. I already alluded to global warming and energy and in the environment and poverty, and you can run through the problems that people are worried about, disease, and it's really only these emerging information technologies that have the scale to address those problems, but it is going to introduce new problems along the way. Each of these technologies have existential downsides. There was some allusion to that in some of the earlier discussions. Biotech, which is perhaps the most mature, the ability to reprogram the outdated software in our bodies, that is being applied to making progress on diseases like cancer, which is a genetic disease. But it also can be applied for destructive purposes. A bioterrorist is also empowered to reprogram a biological virus, to create a new virus that is more deadly, more communicable, or more stealthy. And in fact, we've always used technology to amplify our creative abilities and our destructive abilities. Ever since we had stone tools and fire and iron and so on have been used to amplify our destructiveness. The good news, though, and this does then postulate an ethical guideline is we have the tools to actually protect ourselves from the existential danger I just mentioned. Key to that is being able to sequence a virus quickly. It took us 5 years to sequence HIV. We sequenced SARS in only 31 days. We can now sequence a virus in 1 or 2 days. That's another example of this exponential progression. And RNA interference can turn viruses off because viruses are genes. They just happen to be pathological ones in general. And so I've actually been consulting with the Army. I'm on the Army Science Advisory Board, and and the Army is the agency responsible for bioterrorism protection. And there is underway development there and in other places, a rapid response system that when a new biological virus is detected, it can be sequenced rapidly, and RNA interference medication can be created, as well as new forms of vaccine technologies that just respond to the antigens on the surface of a virus, so they're safe because they don't include the whole virus, and then some new ways of gearing up production and testing these rapidly. Basically, we need to set up what we set up very successfully with software viruses. I mean, every day people put out destructive software viruses, and they're not just games. I mean, we do rely on software to fly airplanes and run intensive care units and 9/11 response systems, and we need software to work reliably. New software viruses are detected. They're reverse engineered. An antiviral program is coded. A lot of that is done automatically. It's then spread virally over the internet. Within 24 hours, generally, we have some protection from a new software virus. And you can argue whether it's working well or not, but actually nobody's taken down even a portion of the internet for 1 second over the last 10 years. It is a pretty effective immune system, technological immune system that we've set up. So that's a basic message at a high level, that we need to develop these defensive systems for these new technologies, as well as having ethical standards for responsible practitioners, like the Asilomar guidelines, which have actually worked very successfully to prevent any accidental problems from biotechnology. And the number of accidental problems has been zero over the last 25 years. Justin Ratner pointed out that paradigms lead to new paradigms, and if you took a narrow definition of Moore's law, it's already ended, but that didn't stop the exponential progression. There were shrinking vacuum tubes in the 1950s after CBS predicted the election of Eisenhower in 1952. That hit a wall. They couldn't shrink the vacuum tube anymore and keep the vacuum, and that was the end of the exponential shrinking of vacuum tubes, but it was not the end of the exponential growth of computing. And we're going to go from one paradigm to another, and this law of accelerating returns is affecting an ever-widening array of technologies. Eric Baum talked about AI as a grab bag of techniques. That's true of the brain as well. The brain is actually a very ornate organization of different information processing organs that evolved through its own peculiar path, but we are taking it apart, and it is a grand project. It's perhaps the most complicated project we've done, but it's not an infinitely complex project. We talked earlier about the amount of genetic data in the design of the brain, and admittedly, there's not a simple mapping between genes and brain structure, but we can see there's massive redundancy in how the brain is organized. Dharmendra Mota said to create the mind, we have to simulate it by reverse engineering it, that neuroscience has matured. And he talked about an alternative to synapse by synapse simulation, which is functional simulation. And this is also very promising, which is to treat a whole region of the brain, not necessarily simulate it synapse by synapse, but to actually try to understand what that region is doing. And that's actually a very effective approach, at least for many of the regions of the brain. If you wanted to simulate a pancreas, you wouldn't simulate the whole biochemistry of every pancreatic islet cell. You would treat the pancreas as one system that has a certain algorithm that responds to glucose and puts out insulin in a certain fashion. It's actually a fairly intricate algorithm, but it's one algorithm despite the fact that there are hundreds of millions of cells involved. And we see a similar thing. It says a region of the brain that processes the temporal relationship of the sound from the two ears and creates a three-dimensional concept of sound. And we understand that algorithm, and we don't have to simulate every neuron to do that. In terms of Ben Goertzel, I'll mention that he and I are working together and with Novamente on a new version of a chatbot for Ramona on our website. And it has some interesting properties. It'll be tied into Wikipedia through the PowerSet technology and also incorporates a number of other open source knowledge sources. So in some ways, she'll be smarter than a person today in that you can ask her about, and this will be out early next year, any movie that's on Wikipedia, or any historical figure, or any event, or any book, and she'll have something knowledgeable to say about it. You'll still be able to trip her up because she does not have human-level understanding of language. In fact, it's simulating semantics rather than really understanding it. We actually hope to go on to actually do some real in-depth processing of semantics. But it brings up an interesting issue that computers are going to have to dumb themselves down to pass the Turing test. Because if they didn't, in fact, we've talked about submitting her to the annual Loebner Turing test, and the major project there will be, in fact, to dumb herself down, because if she has something intelligent to say about every movie and every book, it'll be clear that she's a computer. And so even when computers, in fact, have human levels of knowledge in terms of the ability to handle hierarchical knowledge and language and so on, they're still going to have to dumb themselves down in terms of not knowing everything. And that's a key issue that's not been recognized. Marshall Brain talked about jobs. You know, if I were a prescient futurist in 1900, I'd say, okay, a third of you work in factories and a third of you work on farms. Well, 100 years from now, in the year 2000, that's going to be 3% and 3%, and you go, oh my God, we're all going to be unemployed. And I'd say, well, don't worry, you're going to get jobs as web designers and chip technology designers and a lot of other things, social network entrepreneurs. You wouldn't know what I was talking about. We have managed, in fact, to increase employment, including very recently. If you look at all the jobs that are going to go away, it always looks very daunting, but we've managed to keep up with it. And the new job, in terms of pay, the new jobs actually pay 8 times as much as they did 100 years ago in constant dollars. Ultimately, we are going to make ourselves more intelligent. There may be dislocations along the way, but so far so good. Cynthia Brazil talked about capturing and recreating emotional intelligence, and I would agree with her that that is the cutting edge of human intelligence. In terms of logical analysis and solving puzzles or solving mathematical theorems and doing a broad variety of logical analysis, including access now to increasingly sophisticated knowledge bases, computers already do arguably a superior job to people. Emotion, getting the joke, being funny, understanding irony, as we discussed earlier, that is the cutting edge of human intelligence. And we've identified certain cells, actually, for example, the spindle cells, which only a few species have. We have them, apes have them, we have more than apes. Whales have them, and they have actually more than we do. But and those cells are unusual in that they're deeply interconnected. They span the entire brain. They have not just thousands, but hundreds of thousands, sometimes millions of interconnections, and touch many different regions. And so we're going to have to reverse engineer the regions that it touches on, like the cerebral cortex, before we can actually fully understand what the spindle cells are doing. Peter Stepp talked about rationalization of death as the primary contribution of religious philosophies. I will say there's one good idea from religion, which is pretty pervasive, which is the golden rule. And as I look at the primary work that religions do, that's something we ought to keep. I talked about overload, but actually we've been able to keep up with that. I do not think we're overloaded. We are improving our intelligence even if we haven't put too many computers in our brains yet, through network effects, through the ability to tap into the wisdom of crowds. rather than the wisdom of lynch mobs, which in fact this decentralized communication allows us to do. We have access to tools in our hands that accesses all of human knowledge. Very few people today could do their jobs without the enhancements of intelligence that our tools allow us to do. And Neil talked about this key issue that we are taking reality and using physics to create computers, and then we're also taking computers and creating new forms of reality. Second Life is just a harbinger of things to come, and even though it's on screen in front of you and it's not full immersion and it's cartoon-like, it's already pretty compelling for some people. It's about the size of Shanghai today. It's about 15, 16 million people, and it's not a game to everybody. I know people that actually take it quite seriously, or take it quite seriously that their spouse has a romantic relationship with somebody on Second Life. And so it's the primary issue that we're going to recreate, and ultimately virtual reality is going to be where we spend a lot of our time, because it will become full immersion. It's going to become highly realistic. It has the advantage that you can create new virtual environments much more easily than you can create them in real reality. You can be someone else in virtual reality, and just from a practical point of view, you can communicate with other people. The telephone is virtual reality for the auditory sense. So, which is really the primary story? Creating reality from computers or creating computers from reality? And we've actually debated this energetically ever since David Dalrymple, who's this child prodigy that Neil and I have mentored, brought it up. And Neil left out his punchline and asked me to be sure to mention it, which is, both things are happening simultaneously, and both are going to contribute to the coming profound changes. He alluded to the basic theorem of information, which is really important if you think about it, because analog computers, the longer you run them and the more you process information on them, the less reliable the information becomes. And if you think about the idea of taking billions of bytes of information and then transforming them and moving them around, and if there's an error rate, you would think that that error rate would propagate and get worse. But the basic theorem of information is that with error correcting codes and so on, you can engineer very easily any degree of reliability. You can make the error rate 1 in a trillion if you want, have no error rate to speak of, just by adding enough error codes. And if it weren't for that, we wouldn't be here today, because computers would be impossible. And he also talked about the Fab Lab, and right now they're working at the micron scale with milliscale devices. What we really want to create are micro devices engineered at the nanoscale, and he has a whole roadmap to go from the microscale to the nanoscale in terms of being able to ultimately create compact devices that can produce objects on demand. If I want to send you a movie today or a book or a sound recording, I can just send you an email attachment. Those used to be physical products. And in the future, we're going to send email attachments that can be turned into a wide variety of physical products by reorganizing fragments of matter in input stocks, basically reorganizing things at the molecular level. And the Fab Lab is one roadmap to that. There are others, and that's really only about 20 years away. So I can email you a blouse or a solar panel or a module to build housing, and those visions are not that far away. And he also mentioned that quantum computing does not appear to be needed, that to emulate the human brain appears to be a classical device. Peter, he talked about zero-G. I just had a zero-G experience, and it was really quite cool and profound to transcend something that I've lived with ever since I was born, which is gravity. And that is really what I think human beings are all about. We transcend our limitations. We didn't stay on the ground, we didn't stay on the planet. We have not stayed with the limitations of our biology. Even though biology just became an information technology, we have made progress Human life expectancy was in the 20s 1,000 years ago. It was 37 in 1800. There was no sanitation, no antibiotics. We do transcend, and that's really what we're all about. And I've been very gratified to work with Peter on the X Prize Foundation. We're going to be having prizes in areas like artificial intelligence and life extension to really focus the world's creativity, at least using the prize methodology on those issues. And we're working now on Singularity University. This is an idea that has kind of created itself. That's kind of like how all these projects get started. But it has attracted a lot of both intellectual content and sponsorship in terms of financial resources. So let me quickly actually just show you some slides, which are new ones that we've put together for this conference. And I'm going to skip a lot of slides to, well, this one's worth commenting on, which is that the ongoing exponential is a series of S-curves, and that exponential growth doesn't go on forever. 2 rabbits in Australia become 4, 8, 16, but they do ultimately eat up all the foliage. And that happens with these information technologies as well. They run out of resources, but they create the next paradigm. And we've seen that. This is new in terms of that before it only went to 2002. It's now through 2007. And it really is quite interesting. I mean, this goes back to the 1890 census. And it's pretty remarkable given all the history and dislocations, both wars and economic dislocations that have occurred in the 20th century. And it has continued right on pace. And in my book that I wrote in the late 1990s, Age of Spiritual Machines, I predicted that in the year 2009, you could buy a board for $1,000 that would have a teraflop of computing. That came out just recently, so we're a few months ahead of schedule. But this has gone on, long before Gordon Moore was born, and through many different paradigms. And it's pretty amazing to me as to how inexorable this is. A logarithmic graph like this hides the scale, because this represents trillions-fold of improvement through the 20th century. And you can see it's actually another exponential, because a straight line on a logarithmic graph is exponential growth, and there's been slow exponential growth in the rate of exponential growth. It took 3 years to double the price performance of computing in 1900, 2 years in 1950. It was 12 months in the year 2000. It's 11 months now. And these are different computers, actually from Hans Moravec, but it's the same curve. And, well, actually, wait a second. This is updated, random access memory, marching along. Average transistor price. Okay, this has been updated from 2002 to 2008. Again, it's right on track. And I mean, look at how smooth and predictable a curve this is. And this, again, is not some, this isn't just Intel's plan. I mean, this is the competition of thousands of companies and hundreds of thousands of researchers around the world. And okay, this is also marched on. There's basically a 50% deflation rate in information technology, whether you're talking about bits or transistors or genetic data or brain data, different kinds of databases. There's a 50% deflation rate in information technology. And there's been concern expressed by economists that that'll lead to deflation as information technology dominates more and more of the economy. It will be most of the economy in the 2020s. And if you can get, and when we have desktop nanofactories that can create most, if not, and eventually all of the physical products you need in your life from information files and very inexpensive input materials, and everything is information technology. And if that has a 50% deflation rate, you're not going to actually double your consumption year after year of basically everything to keep up with this doubling of price performance. So the size of the economy as measured in constant currencies will shrink. For a variety of actually good reasons, that would not be a good thing. But that's actually not what we see. We more than double our consumption. There's been 18% growth in constant dollars in every form of information technology for the last half century, despite the fact you can get twice as much stuff for the same amount of money each year. And the reason for that is as price performance reaches certain levels, whole new applications explode. And people didn't buy iPods for $10,000, which is what it would have cost 12 years ago. And again, it's a very smooth curve. This is bits shipped, but you can look at other forms of information technology. This has just been updated, and it's still right on track. Magnetic data storage, this is updated. I just put this up because it's not Moore's law. I mean, it's different engineers, different engineering problems, shrinking magnetic spots on a magnetic substrate. It's not shrinking transistor sizes on an integrated circuit, but we see the same kind of exponential progression on this logarithmic graph. DNA sequencing cost is coming down exponentially. The first genome cost $1 billion. It cost $10 per base pair in 1990. It's a small fraction of a penny today. We're pretty close to a $10,000 genome. It'll be $1,000 a few years later. And the amount of genetic data keeps growing at an exponential pace. And communication technologies are growing similarly. Okay, we haven't updated this yet, but I had a little bit of this curve in the 1980s, the ARPANET, and it has continued to grow at an exponential pace. So I'll stop there, but just to make the point that more and more technologies are becoming information technologies. So the purview of this law of accelerating returns is expanding, and it doesn't all stem from electronics. And as a technology becomes an information technology, it is subject to this exponential progression. A very exciting development is that health and medicine has just become an information technology. I mean, as of a few years ago, we didn't have the genome, we didn't have means of changing the genes, we didn't have means of simulating biology. All of that has changed. And although it's in an early stage, these technologies will be 1,000 times more powerful in 10 years, 1,000,000 times more powerful in 20 years, and it will be, I think, a very exciting horizon. And it's really only these technologies that have the scale to solve the problems that face humanity. And we will create new problems at a subtle level, things like privacy and equal distribution, and what are we going to do with jobs and so on. And at a profound level in terms of new existential risks to humanity, it's on these issues that we need to focus our attention, whereas I think the progressions appear to be inexorable. What we do with these new powers is not. So the history of the future has not yet been written, and I think for people such as all of you who are aware of these growing powers of information technology and growing purview of information technology, it's incumbent on us to guide these technologies in constructive directions that support our human values, even though it may seem that we don't always have a consensus on what those values are. I actually think we do. It actually comes back to religion, which is applying the golden rule. Thank you very much.
Yes, we'll introduce her. Can you thanks for the sake
Do we have time for a question or two? Okay, time for one or two questions. Yes?
Can you speak to the rate of new areas becoming IT-ified?
Well, nanotechnology is a big one, and that's in an early stage. A lot of what goes for nanotechnology is really creating new materials, and it's become a marketing buzzword where it isn't always an information technology. But, and I would say the real era where information-based nanotechnology is a reality is still a number of years off. The golden age of that will be in about 15 to 20 years. And that then will transform lots of things. But it's already transforming, for example, energy. Actually, let me show you those slides because they're later on in this presentation. Can we activate this again? Okay. But health and medicine is a big one. I mean, that's 25% of our GDP and a lot of our concern. Actually, let me comment on this, which I alluded to earlier, but this is the Mandelbrot set, and you can see fantastically complex images on the web, but it's actually only 6 bytes of design information. And it's a similar issue with the brain, because the brain is a probabilistic recursive fractal, and it's more than 6 bytes. It's, by my estimate, 25 to 50 million bytes. That's not simple, but it's a level of complexity that we can handle. So this is the most relevant slide. This is exponential growth and the amount, this cumulative photovoltaic production. We, in fact, are using the ones that have been produced. The amount of energy we're getting out of solar energy is doubling every 2 years and has been for about 20 years. And it's about 8 doublings away from meeting 100% of our energy needs. And what's driving it is this reduction in the cost. And fossil fuels are going the other way. The crossover is really only about 5 years away. One last question?
Who ideally do you think should take responsibility for the risks associated with these emerging technologies?
Well, I think, we live in a democracy, so everybody should take advantage of it. Practitioners are close to a particular technology. It's incumbent upon them to both practice ethical guidelines, and biotech actually established a good precedent for that with the Asilomar guidelines, which have been made more and more sophisticated and have worked really well for accidental problems. In terms of intentional abuse, that's something that, again, practitioners who are knowledgeable should get involved, and general citizens should get involved in lobbying governments to do something about that. There is an existential risk now from biotechnology, and so some people, for example, Bill McKibben, who came up with the term global warming, and I have a lot of respect for him as an environmentalist, but he wrote a book saying enough, meaning enough already with advanced technology, and we should relinquish biotechnology because of this danger. And that's a bad idea for 3 reasons. First of all, it would deprive us of the profound benefits that we are going to get. Secondly, it would require a totalitarian system to implement. And thirdly, it wouldn't work. It would just drive these technologies underground where they'd be even more out of control. And the responsible practitioners that we need to have easy access to the tools to protect us would be deprived of that access. So the real answer is these ethical guidelines and putting a high priority in developing the defensive systems. And given that we live in a democracy and informed citizenry on these issues, I think it's very important. Thank you very much.